Okay, we move into our closing chapter on optics with light and interference and eventually diffraction. So first of all, let's talk about the scientists involved in this discussion. The competing theories on light were between Sir Isaac Newton, 1643 to 1727, and Christian Huygens, 1629 to 1695. So they were essentially contemporaries. Huygens was a little bit older than Newton. They each had different ideas of what was happening with light. And Isaac Newton speculated that we called it his corpuscle theory, corpuscles being little objects of particles of light. He said that light consisted of many small particles. Using his theory, he was able to describe reflection. Think of something kind of bouncing in, bouncing off. Angle of incidence is angle of reflection. Refraction, he described, and I'll talk about that more in a minute, but he described refraction as something where when a particle goes into water, it actually speeds up, goes faster, and that's why he said that ray would go closer to the normal. He said that the particle theory supports the fact that light travels in straight lines, and that when we see light and we can see these sharp shadows, that just is more definition, more proof that light is a particle. So Christian Huygens, who was a Dutch scientist, speculated that light might be a wave, and he was able to explain reflection and refraction through his wave theory. So let's take a look at what his theory was again, just so we can review it. The idea is if you had this little semicircle A prime, each little point on the semicircle would be considered a source for a new little wavelet. So if you get a compass and you start with that point, you could make another little arc. And when you get all of these overlapping arcs, one on top of another, it creates another wave form, which would be the semicircle B prime. So his idea of having these little wavelets would be able to describe wave propagation. Using his principle, he could explain both reflection and refraction. In the first case is reflection, right? As the waves come in, they bounce, and then they go off. Angle of incidence equals angle of reflection. And then, in part B, as you're approaching water, once you get into water, you slow down, and that slowing down causes you to bend towards the normal. So the wavefront actually bends. In any case, Huygens could explain light as a wave. It was using light was a wave. He was able to explain both reflection and refraction. So here's just a side-by-side comparison. The particle idea behind reflection, particles would just bounce off, and so would waves. And then refraction was slightly different. Newton thought that the particles would be pulled because of some sort of gravitational attraction, so that they would be going faster through the medium, and that's why they would go closer to normal. And then Huygens postulated that no, it was going slower, and that's why it was refracting through the medium. Well, Newton prevailed at the time because he was famous, and everybody expected that he would be right. Definitely more well-known, well-established as a scientist than Huygens was. And he figured that the sharp-edged shadows gave proof that his corpuscular model was correct. And that was true until about 1802, when Thomas Young, who was so this is many 100 years later, right? Thomas Young was a British scientist and physician. He had played around with a lot of studying light, especially Newton's theories on color and breaking white light into its component colors. He was the one who postulated that all the colors could be reduced to just 3. Anyway, in studying light, he started to realize and conceive the fact that it was very similar to sound. It tended to, it seemed to have, anyway, wave-like properties, and so he wanted to test it. So he came up with a truly ingenious experiment, and he figured that if light was a wave, then it should interfere, because that's one of the properties of waves. We get constructive interference and destructive interference, like you have standing waves in pipes with sound, that you could do something similar with light, that you could get interference and you could get diffraction also. That's another property we hadn't really talked about before, but a property that is characteristic of light. So it would exhibit these properties. Now, how do you get light to interfere? The problem is the wavelength is so small, it's hard to perceive of any kind of interference. So just a quick review of interference. When waves overlap, they will interfere. When a crest meets a crest, then you have constructive interference. And then when a crest meets a trough, you're going to get a destructive interference. So this one would be constructive, and then they cancel out. This is like a partial cancellation. Then they're going to be destructive. In order to get waves to interfere, they have to have the same wavelength. So you start with that. Two different waves, same wavelength, and you can see how they interfere. The phase difference between them doesn't change, then you can get them in phase, and crests are going to line up with crests, and or if they're out of phase, then crests are going to line up with troughs, but they're going to be constantly lining up that way. Now the problem that Young faced is that light is made up of many, many wavelengths, so it was tricky to isolate into a monochromatic or one wavelength type of a light source. When you have monochromatic light, and that is in phase, then you have coherent light. And that's what he needed, was coherent light in order to check and test for interference. Now that would have been handy if he had lasers, but they had not yet been invented, so he didn't have that ability. So let's think about what might happen if light waves are going to interfere. So this is a picture of water waves. He figured that if light was a wave, it would interfere much the way that water waves would. So he wanted to come up with an experiment like one like this with water waves. And the idea of this experiment is you have two little sources here, one here, and they're bobbing up and down, and each of them is putting little ripples in the water. And as the ripples travel away, so the ripples are kind of traveling out this way, as the ripples travel away, then the ripple from one overlaps with the ripple from the other, and you get this constructive and destructive interference. The little yellow spots represent, or the yellow lines represent what we call null spots or nodes. That's where one trough has interfered with one crest and nullified each other. And then in between, we call the bright spots. That's where the two crests overlap with each other, creating an antinode. Okay, so those red lines would represent the bright spots, and then the yellow lines would represent the nodes or the null spots. So if you were looking over here at this edge, you would see this pattern of bright, dark, bright, dark, bright, dark, bright, dark, a little variation on the far side. So here is this dizzying looking picture, but the idea is that from point source A, if you have something going up and down, you're going to have these little wavelets that tend to move away, and the same wavelength for B. Okay, and where those waves overlap, you get these crests meets crest and crest meets trough. So you're going to get a combination of constructive and destructive interference. Now these red lines that I've just put are where the two sets of ripples overlap, so you're going to get constructive interference. So those would be representing bright spots. Okay, that's what the red lines are. Now the yellow line is where the crest of one wave, so let's look. So we have a wave right here, okay, wave coming in right there. When I look right there, the crest of that wave, it turns out, is meeting the trough of the other wave. So it is, I'm talking on the yellow spot. So I'm in between, I'm on that wave, but then I'm in between the other one. So I'm in the trough of one set of ripples and the crest of the other. And so right there I'm going to get destructive interference. So this yellow line represents all the places where the trough meets the trough. The crest meets the trough, and they destructively interfere. So again, the yellow lines represent null spots, the bright represent bright spots. So if we have a good interference pattern, we're going to see these bright, dark, bright, dark, bright, dark when we shine it on a wall. And that was Young's goal, was to create what he calls an interference pattern. He didn't have coherent light, so his ingenious approach was to start with a light source over here, and he put a single slit. And if you think of Huygen's principle, you know, from that little slit will be many wavelets, and from that created some waves that would come out and away from that one little slit, and then eventually each of those waves would reach a double slit. So we have two, right here and right here. As those waves hit those double slits, then they would set up their own little ripples, and they would move out and progress away. And then we could look for the overlapping crests and the crests with the troughs. And you can see where, let me go back a second, sorry. You can see where our bright spots are going to be where the crest meets crest. right there. And then the null, which I think we had in yellow, are going to represent the crest meets trough. Okay, so you get a bright spot here, and then a dark spot, and you'll get that pattern when you shine it on a wall. That's what you would expect to see if you were getting interference. So he was looking for this. And this is just another diagram that kind of gives you an idea of what's happening. This picture down here is what you might perceive if you're looking to see what's happening. In other words, if you shine a light through first a single slit and then a double slit, okay, those waves work their way through. The red represents like a trough, and the yellow might represent a crest. As they come through here and overlap, then you get this pattern on the far wall that shows bright here, bright here, bright here, and then dark spots in between. So this wavy motion of light and dark, which was what Young was able to show, proved that light must be a wave. So Huygens was right in the end. Newton was wrong. Sort of. Einstein's going to correct that in a couple of years. Like 100 years. Okay, so let's quantify interference. Let's try to describe what's happening mathematically. So here's a little geometry. We have some triangles set up. Now the idea is when you have constructive interference, that means that crest is meeting with crest. So if you have a wave that starts at point A and moves and travels across and over to this spot, okay, and you have a wave that starts over here and it travels this distance, and they come together and meet, the question is it going to be a bright spot there, or is it going to be a dark spot, or is it going to be something in between? So let's look at the math. We have a wave starting from A and we have a wave starting from B. If you set it up so that point P is where the distance that the wave travels along this way, if that distance it travels is exactly one wavelength longer than the distance that these guys are going to travel, you're going to have a constructive interference. They're going to come together and meet at that point, and you're going to get a bright spot. And that's what you're looking for. You're trying to find a place along this line where the two waves come together, where one wave has traveled exactly one wavelength longer than the other. And when they meet, you're going to get a bright spot. So you can say that S, okay, S is this length right here. S is D, here's D, times the sine of theta, right? So that's sine of theta is opposite over hypotenuse. So S is going to be D sine theta. Just do a little trigonometric manipulation. And it turns out that if that is equal to 1 times the wavelength, then you've got constructive interference. Well, you're going to get another one, another point of interference, maybe up here somewhere, where the total distance that it has traveled is 2 wavelengths difference. When you get a 2 wavelength difference, you're going to get another bright spot. And so on. You might get another bright spot up here, where it's 3 wavelengths differential. That one has to go 3 wavelengths further than that. You're going to get another bright spot. So mathematically speaking, you're going to get a whole bunch. They become less visible after the first couple, but anyway. Their first spot is going to be where S is equal to 0. That means the 2 waves come in, they hit together, no problem, interference. Second bright spot is where D sine theta is 1 times the lambda, lambda being the wavelength of the light. The third bright spot, D sine theta, is worth 2 times the lambda. So in other words, you can come up with a general formula. For constructive interference, D sine theta equals m lambda. And when m represents the order of the interference pattern. So the first one you start with is 0, because that's going to be your bright spot. And then the next one is going to be 1, and then 2, and then 3 and 4. We say plus or minus because, let me go back for a second. On this pattern, you're going to have a bright spot up here with the P, but you're going to get another one down here and down below. So you get them above and below. You're going to get bright spots in both places. Okay, so D sine theta equals m lambda. That's a really common equation. All right, destructive interference. Keep in mind, destructive interference, crest meets trough. That's when they're going to be 1/2 wavelength out of phase. So that's what you're looking for in this case. S equals D sine theta is going to be 1/2 lambda. When they're half a wavelength out of phase, they're going to knock each other out, and it's going to become a dark spot. You're going to get destructive interference. So our formula for destructive interference is very similar to constructive, except that you're going to get it at a 1/2 wavelength, and then the next one will be at 3/2 of a wavelength, and then 5/2, because every time you're off by 1/2 They'll cancel each other out. So our destructive interference formula looks like this. D sin theta is m plus 1/2 lambda. So you have to really pay attention when you're doing your lab, for example, to say, are you looking for a bright spot? That's going to be your constructive interference formula. Or you're looking for a dark spot? That's going to be your destructive interference formula. So you got to know which one you're using under given circumstances. Note the effect. So if you have d sine theta is m lambda, and that's the equation we're going to see again and again and again. D sine theta is m lambda. Then if you solve for d, you're going to get m lambda, not y, m lambda over sine theta. Okay, that's your d relationship. Now check out what happens with the angle, right? As the angle gets bigger, then sine theta gets bigger. So if d is large, okay, as in the case on the left, then theta is small, right? See the relationship, mathematical. If d is large, theta is inversely related, so theta is going to be small. If d is small, then sine theta gets larger, or theta gets larger. Okay, so that's going to be sort of the inverse relationship to be paying attention to. Okay, and that concludes our lecture. Thank you.